So this is Unit 1, Lesson 2. The unit is called Limits and Continuity. The lesson is called Defining Limit Using Limit Notation. In this lesson, we're going to learn how to understand limit notation, how to speak and write limit notation, and how to go about finding a limit. So here's our formal definition. Given a function f, the limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c, but not equal to c. So here we go. Given function f, this red line function f, the limit as f of x approaches x, or as the limit of f of x as x approaches c is some real number r if f of x can be made arbitrarily close to c, but not equal to c. So let's take a look at how to what this limit notation looks like. So it looks like this right here. There's two ways we can say it. We can say the limit of f of x as x approaches c is r. Or we could say the limit as x approaches c of f of x is r. There's not much difference in those. You're going to hear me talking the limit as x approaches c of f of x is r more often than not, but it doesn't really matter. So both are good. Let's look at an example. So number one, write a function g of x. A function g of x is modeling behavior around the value x equals 3. It is found that the limit as x approaches 3 of g of x equals 17. Write this limit as a sentence. Well, as I just said, there's two ways we can do this. We could say, I'm going to say it this way. The limit as x approaches 3 of g of x is 17. The other way would be the limit as x approaches, the limit of g of x as x approaches 3 is 17. Number 2, it is found that h of t can be made arbitrarily close to 7 by making t arbitrarily close to 5. Write this relationship in as a mathematical statement. And so what we're doing is taking t arbitrarily close to 5, which means we're finding the limit as t approaches 5. And it is found that h of t can be made arbitrarily close to 7. So we're going to say the limit as t approaches 5 of h of t equals 7. And that's that. So here's an example looking at a graph, and just gonna call out the elephant right here. What is that? And so that's called a hole. We're gonna get to that later in the road. I'm just throwing this in here just so you see it and get comfortable with it, because it's gonna be showing up a lot. It's not going away. So anyways, from the graph of s of x, what do you suspect is the value at the limit as x approaches 3 of s of x? Well, as we come from the left and work our way towards x equals 3, we hit this hole, and then we start coming down, and we approach the value of 1 and 1/2. From the right, and we work our way towards the left, towards 3, we find that we go up to about 1.1 and 1/2. And so we're going to say, because from the left and from the right, both sides approach 1 and 1/2 at t equals 3, we're going to say the limit is 1 and 1/2. It's important to point out that the left side and the right side both have to be approaching the same limit for the limit to exist in the first place. I'll say that one more time. It's very important that the limit from the left and the limit from the right both be approaching the same, in this case, s value. If they're not, then the limit does not exist, and we'll get more into that in a little bit. All right, so here's from a table. So from the table, of values q of t shown, which of the following is most likely the value of the limit as t approaches 2 of q of t? And so now we look, we've got 1.9, 1.95, 1.99. So for the first three values, our t value is going up and it's approaching 2. As we do that, we see our q of t values are approaching negative 3.5. And it looks like we're kind of plateauing there. And then we have on the right, we have 2.1, 2.05, and 2.01 for our t-values. So from the right, and we work our way towards 2, we see that the Q of t-values are also approaching negative 3.5. So from the left, we're approaching negative 3.5. From the right, we're approaching negative 3.5. So we're going to say the limit as t approaches 2 of Q of t is negative 3.5. So C is our best answer for this one. All right, let's look at some representations for the limit notation. It is found that as x approaches pi, corresponding values of a function L of x approach the value e. Which of the following is an equivalent statement? So let's take this piece by piece. First of all, a and b are not even limit notation. Not even limit notation. So we're just going to omit those two as possible answers. They're not even limits. If we look at the statement, as x approaches pi, so we're looking for a statement that starts off with the limit as x approaches pi. And so we can see D has a limit as x approaches pi, and G also has a limit as x approaches pi. And so for that reason, we can eliminate C as an option. We can eliminate E, F, and H. And now we also see that function L of x approaches the value E. So we're looking for L of x is E. So for D, again, we also have L of x is E. So the limit as x approaches pi of L of x is E. And for E, we also have L of x is E. Which means we can eliminate G. And since we've already eliminated E, we can say that D is the best answer. So this shows x approaching pi. The corresponding values of a function L of x approach the value E. All right, so some takeaways for this lesson. We don't know everything yet, and Mr. Jansen's has been throwing this stuff at you like crazy fast, but we know more than we did 2 lessons ago. Limit notation is very important. We're going to use it all the time for the next few weeks, so we're going to get very good at it. It takes some work, but once we get the hang of it, it's not that bad. Using tables, we can get a pretty good estimate of limit, but it doesn't quite confirm the limit exactly. We haven't gotten to that point yet. And then also takeaway, why did that graph have a hole in it? And we're going to unpack that in the next lesson.